another Avogadro's number type problem. We're just moving in a different direction in the flow chart. So instead of going from mass to atom, in this problem, we are asked to find the mass, right? What is the mass in grams of a single neon atom? So if we could set up a scale, if we could develop the technology that was sensitive enough to the point that if we placed a single neon atom on top of that scale, what mass reading would it give us? Well, we actually don't even need a scale to figure this out, right? We can use the same type of calculations that we just learned, just in the reverse direction. Instead of going, to go back to our flowchart again, boop, instead of going from mass to atom, we are now starting with one atom. We can use Avogadro's number to figure out how many moles this one atom is equal to. And we can use the molar mass of neon to figure out what the mass of that atom is. Because we know the identity of the atom is neon. Well, Avogadro's number doesn't really care about the identity of your substance, molar mass does. So if we know Avogadro's number, which we do, and if we know the molar mass of the element we're working with, which we can find, we can figure out what its mass is. All right, so now that I've shown you how to set up the flowchart, we've already seen one example problem together. Again, I'm going to encourage you to try and set up this calculation yourself. Starting with one atom of neon, use the conversion factors at your disposal, put both of them together, and find what the mass of your neon atom is. Okay, now we are going to come back together. Welcome back from unpausing. And if you never pause these videos, again, I'm going to encourage you to. It's a really good habit to get into when presented with a new idea, to see if you can't try it out for yourself. See if your brain can't wrap itself around. And if it can't, if you can't quite get to the right answer, or if your answer you feel is kind of off, that's fine too. That's why we double check our work together. So yes, let's come back together, set up our calculation for the mass of one single neon atom. Just like before, we're gonna start with what we know. Single neon atom means that we are starting with one neon atom. One neon atom. We are going to convert the unit of the atom into the unit of the mole using Avogadro's number. It's just going to be presented in the inverse way compared to the previous problem that we have done. So we are going to keep the 6.022 times 10 to the 23rd, since this is where the atom count is. We're going to put this in the denominator, make sure that we are getting away from where we were, and we're going to put the 1 mole up on top, since this is the direction we are trying to move in according to our flowchart. All right, and once we are in the unit of the mole, all we have to do is check out the periodic table to find what the mass of a single neon atom is. We check out the periodic table, we would find that the mass is 20.18 grams per every 1 mole of neon. Right, so this is where this value comes from. The 20.18, again, is in the unit of grams per mole. So we're keeping the 20.18 with the gram. The mole is on the opposite side of the divisional line. Since we're trying to get out of the mole, that's going to go on bottom. We can see moles now we're going to cancel out, since we have 1 in the numerator, 1 in the denominator. And the only unit that remains is the gram, which is the direction we are trying to move in. I'm actually going to rewrite it down here. There's more space down here. So if we crunch these numbers, what is the mass of the single neon atom? The mass of a single neon atom is 3.351 times 10 to the negative 23 grams. Right, so this is a super tiny mass. It's like 0.0000. Basically, we have 22 zeros in a row before we hit 3351. Now, the answer I have written here also has 4 significant figures. We can see that the number that we started with is actually a perfect integer, right? 1 is a perfect counting number. Perfect. Which means it doesn't really have applicable sig figs. So we're going to have to look at the conversion factors over here. in order to figure out what our number of significant figures is going to be. Well, Avogadro's number, again, is a measured conversion factor. It is approximate, it's an average. So we have 4 significant figures present here, as well as the mass from the periodic table also has 4 significant figures. And so since both of our conversion factors have 4 sig figs, our answer should also be presented with 4 sig figs. So 3.351 times 10 to the negative 23rd grams.